Hello, I'm Thor. I work on cryptography at a project called Entropy. We're a decentralized asset custodian. In particular, we've been working on implementing a protocol called GG20, Gennaro Goldfeder 20, a threshold signature protocol from a pair of cryptographers in New York. So yeah, this is my talk. So a good thing to do is that there's going to be a HackMD document that you can kind of use to catch up on things that you didn't quite get, or you can follow up with me on Twitter. So if you pull your phones out and scan the QR code right there, that should get you a document that sort of explains a lot of stuff that I'm about to talk about in slightly greater detail, because there will be math at the end and it will suck. Just kidding, it's really cool math, but you probably won't get it on the first pass. So yeah. All right. Yeah, we can. So, gonna keep dancing. It's an awkward dance, but it's a dance nonetheless. All right, going once. Going once more. All right, I see no more phones, so I'm gonna take that as a signal. And what is an ECDSA? So I'm going to kind of like roll back here. I think we sort of make a lot of assumptions about what people do and don't know. And so when I say words like ECDSA, I think that a lot of people are like, yeah, this is basic, but I think some people might not know. So the general way we think about like cryptography is like we're trying to prevent someone from doing something. In this case, we're trying to prevent someone that's not you from pretending to be you. So we have two protocols. We have a signing protocol, which is sign using some secret key on some message, which produces a signature. And then we have a verify protocol, which is you just verify some signature in some message using the user's public key, and it says, yeah, that is the user, or no, that's someone else. So the usual signing protocol that we use in cryptography, especially in blockchains, because it produces short signatures, which space really matters, and fast run times to verify stuff, is an ECDSA, which is an elliptic curve digital signature algorithm. And that's sort of a riff off of a protocol that was invented in the 70s or maybe early 80s by a pair of cryptographers named Martin Hellman and Walt Diffie, or Whit Diffie. So Alice takes her secret key in a message and signs the message. And that's pretty much all it is. It produces a signature, and the verifier can then come in. Bob says, okay, so I've got a private key, or I've got a public key from Alice and a message and her signature. I'm going to verify it. And 1, yes, it is Alice. And 0, no, it's not Alice. So that's pretty important to understand the rest of the talk. Because we're going to be talking about other kinds of signatures now. We've unlocked a multi-signature. So a multi-signature is really just, you need a trusted verifier, like Wells Fargo, to say, okay, have at least T plus 1 people sign something. So if Alice, Bob, and Carol are going to come in and say, we're going to sign some message, like a transaction, and we have a trusted verifier. Traditionally, this is a big centralized party who everyone trusts, like Wells Fargo. And the neat thing that we figured out how to do with blockchains is that we got rid of Wells Fargo and put a smart contract in there. So a multi-signature just says, if I want a group of people to collaborate on signing a message, like for instance a transaction, we're going to collect at least some signatures, and the smart contract, which now replaces Wells Fargo or whatever trusted party, is going to verify that some signatures have been signed, and if it gets enough signatures, then it spits out a signature and says, go do the thing. And what's sort of neat about this is that it's really simple. It's just ECDSA with a trusted party, which we use a smart contract for. And since smart contracts do things that we tell them to, we kind of manage to solve the trust problem. So what multi-signatures are good for? If you're using a smart contract, you get this trustless property. You get the T of N property, which is kind of neat because it lets you collaborate with your friends. You get a simple implementation. It's literally just store some signatures, and if you get enough signatures, go do the thing. And it's offline. So that means that all parties can be offline, or sorry, all parties can interact asynchronously with the trusted party. So Alice comes in and says, I would like to sign this today. Bob's asleep or in Amsterdam or jet lagged or something. And he comes in and says, OK, I'm a day later, and I'm going to sign it. Alice and Bob did not have to be online at the same time. And what's lame about a multi-signature that we might like to do better is it's kind of space inefficient. So if you think, OK, so we're all like computer science or computer science adjacent. So we're going to think about like costs. Like we could do better because space on a blockchain is expensive. And blockchain computation is expensive, and since our smart contract is doing all the verification and all the storage of these signatures, for every transaction that gets signed, that smart contract needs to do. It needs to store T signatures, which that doesn't sound like a lot of data, but it's kind of a lot of data over time if that's like every transaction. So it's kind of inefficient in both a sort of space sense. You have to store T signatures for every one signature produced. And it's verifier inefficient because you have to verify T signatures for every one signature produced. So how do we do better? With memes. No, just kidding, with math. We're going to use cryptography. Yay, I have a job. And we are going to try to make a protocol where we sacrifice on the online property or the offline property. So the new protocol, we're going to have Alice and Bob, or Alice and Carol, or Bob and Carol, come together and say, well, let's all do something and produce only a single signature. Now there's not even like a smart contract in the mix. They're just going to all talk to each other and try to sign a single message. And if Alice and Bob and Carol like all trust each other, then they might all just like share a private key, but that's obviously pretty shit. So we really would like them each to have like their own secret, their own little secret key, and say, well, if you can all do something that produces a valid signature together, then we only produce one signature, so we solved space and verifier efficiency. But they all have to be online. So if we wander on, that is what a threshold signature is. So threshold signatures, we keep the T of n property that we got with multi-signatures. Insofar as you trust the process, it's trustless if our protocol works. It does not have a simple implementation in most sort of envisionings of this, because they all need to like convince each other of something without revealing their secrets. And it's not offline, but we win space efficiency and verifier efficiency. And a threshold signature is composed of two new protocols that are not included in traditional signatures, which we need to generate keys, and we need to sign a message. Now, this is in a ECDSA context, or just a normal signature context. Everyone's like, I'm going to pick a random value, and that's my key, which works great, but you can't do it easily in the threshold ECDSA context, because it turns out everyone needs to know a little something about everyone else's key, but not enough to recover it. So we're going to get to keygen in this talk, and signing is kind of a whole nother ball game, and I don't think I'll have enough time to talk about it in 30 minutes. But you're welcome to talk to me about it afterwards. Please talk to me. So we're going to share some secrets. You tell me yours first. With Shamir secret sharing, which is kind of like the grand poobah of information theoretic secure secret sharing, in that there's a lot of ways for you to like share a little bit about your secret, but we generally talk about like, what does it mean that you know something about my thing without being able to recover my thing? It means that you would do no better than a coin flip if it was like guessing like a binary digit, or if it was like a field of n elements, you would do no better than 1 out of n guess. Even knowing something about it, it gives you no like ability to guess what the thing is. No advantage. So how can Alice construct shares of her secret? And she wants to send some shares to her friends. And the thing that we might try is we might observe that, well, polynomials are pretty cool. And linear algebra is pretty neat. And we, being humble nerds of math, know a thing or two about polynomials. We know that if you have a degree 1 polynomial that is a line, you need 2 points to reconstruct the line, any 2 points. If there's a third point, it will also be on the line, but you don't need the third point to reconstruct the line. That's a degree 1 polynomial. It's like f of x equals u plus a1x, just some line. And if we have a degree 2 polynomial, we need 3 points. And my voice is going up because the number is going up. Important. So if we have like a parabola, a degree 2 polynomial, we need to grab 3 points, and then we can reconstruct that parabola. But if we only had 2 points, we wouldn't be able to reconstruct that parabola. Or if we only had 1 point, we wouldn't be able to reconstruct the line. That has left us an exercise to the reader, but you should verify that you understand this. And if you want to know how to do this, like holy rigor, max rigor with like any level of like degree, like maybe it's the 23rd degree polynomial, which would allow you to have 22, you need 22 points on this 21st degree polynomial to reconstruct the polynomial. You could do like you need 22 parties out of your like n parties to do your secret sharing thing. And that's basically how we construct secret sharing with Shamir. Oh yeah, and these coefficients are just randomly selected. They really don't matter, because in fact, we're going to encode the secret, not as any of these blue points over here, but just where the point intersects the y-axis. So what does it mean that the point intersects the y-axis? It means that if we plug in 0 for x, then only this u term is going to remain. Like all of these other terms vanish because they all have a factor of x. So we're going to encode our secret with Shamir secret sharing by saying our secret's going to be u. You are my secret. And we're going to use that as a way of doing this threshold signature keygen situation. And so we now have a way to share secrets. And recall that we did through this whole song and dance to convince you that if you have a secret and you have some friends, your friends need to have enough points on this polynomial to reconstruct your secret and find where u is. So Alice is going to have some secret u as before. And she's going to construct some polynomial, u plus some coefficient times x times some other coefficient times x squared, by typo. And we're going to do 2 of 4 secret sharing. And I'm highlighting that there's confusing terminology here. 2 of 4 sounds like it should be 3 of 4 because you need 3 points, but that's kind of just a terminology fail. So we generally say a 2 of 4 polynomial, or a 2 of 4 secret sharing, or yeah, 2 of 4 threshold signature needs 3 points, not 2, but 4 parties total. There are 4 parties that can participate. You pick any 3 of them. It's a 2 of 4. Sorry. And so Alice is going to send the evaluation, f of 1, f of 2, f of 3. There's no reason that she needs to do any fancy stuff with the integers except for maybe efficient computation. But yeah. And this person knowing what f of 3 is does not tell her anything about what f of 2 is or what f of 1 is. They all know that they have evaluations of some polynomial. And why does this suck? Take a moment to consider if we're trying to do like a key generation situation where everyone has their own secret share and doesn't know anything about anyone else's secret share, why does the above protocol suck? Trusted dealer. Alice still knows everything. So this secret sharing scheme means like, okay, so yeah, if you really trust Alice, Alice is your trusted dealer, you've set up your secret sharing, and maybe Alice is the only one with anything to lose. In that case, yeah, okay, sure. This is pretty simple, it works. But if you wanted to maybe not have a trusted dealer, she knows everything. Hello, bye-bye. I want to go down. Hello. That looks like a good slide. DKG time. DKG is distributed key generation. So Alice knowing everything is not great for every situation. So perhaps we might like to have parties independently generate their keys and tell each other something. And if you haven't pulled up the HackMD, this is about to get to be the mathy slide, so I just thought I'd drop another opportunity to pull that up. I'm going to do a little dance, check for phones. All right, you all look like really smart folks, I believe. And yeah, that's not the writing of someone that needs help. This is writing of someone that's trying to help. Okay, moving on. So, phase one. Secrets. Asked before. Parties 1 through n are going to choose some secrets. We're going to call them u1 through n. And the goal here is that every party is going to have a secret share of some polynomial. And then in the threshold signing phase, they will effectively use their secrets to reconstruct the secret key, the big U, the U that everyone doesn't know anything about. Because we're moving away from Alice knowing you. We're trying to get everyone to have a little part of you, but not anyone knowing what you is. Secrets. So we have parties 1 through n have some share that they generate, u1 through un, randomly. And not important what that is. Oops, bye. And they're going to publish the hiding of their secret. And there are a couple of steps that I'm kind of going to elide here for simplicity and time. But at plenty of stages in this protocol, parties are going to publish things about their share that doesn't reveal the share itself. Like one example of that is the hiding of the share, where we take g, some generator, to the exponent of u1. And to break this hiding, you would need to solve the discrete log problem, which you probably heard about in some computer science class 5 years ago, you're cryptography people. You guys, you all dropped out of high school anyway. Phase 2. So what do we know? Every party has their secret, their temporary secret, I should say, and they're going to calculate the secret sharing. And I'm going to denote that as the capital S function of their secret, ui, and some variable yet to be evaluated. That's going to be the index at which it gets evaluated. And they're going to calculate a bunch of shares to their secret polynomial, Si and Sj. And so they're going to calculate an evaluation Si and Sj for each of the other parties that's playing in the protocol. So now we have parties 1 through n have their secrets as before, the hidings. The pink means that everyone knows it. The blue means that only they know it. And now they have this secret sharing that they've constructed with a bunch of random coefficients, and they're going to send the evaluation of their secret sharing to all of their friends, all of the players that are playing with them. So now they're going to send each other stuff. Everyone's going to have a good party. They're going to talk to each other. They're going to go up to each other, say, hey, how have you been? Here's my secret. Please don't tell other people. And we now have every player has a secret for every other player, and they're going to add them. Yeah, add them. Yeah, add them. They're going to add them. And that makes sense, because if you add a bunch of secrets together, you get a really big secret. That doesn't make sense. But what it does mean is that if we take a look back at the expression of what it means that a secret share looks like stuff. Actually, I'm scrolling down, but it's good enough for me. So this secret sharing of UI, and well, let's wander back up. Yeah, okay. So what does it mean that we're going to say xi is going to be the addition of all of those elements? Xi is going to be their final secret share, by the way. Their original secret share was just a throwaway to get to xi. So xi is going to be the sum of all of the secrets they received from their friends. And we're going to say, look at xi as the sum of some secrets, which is the sum of some secret sharing polynomials, which is, and this is the part that helps to see it on paper or take notes. But what this actually is like we just have a bunch of UJs. We have the sum of all UJs. We have the sum of everyone else's randomly chosen coefficients times I, because everyone sent that person the evaluation of the protocol at I, times blah, blah, blah. And this is actually, if This is a coefficient. This is a coefficient. That's a coefficient. We got back to a secret sharing polynomial. And we all have secret shares of our brand spanking new secret sharing polynomial. And that's pretty neat, because no one else knows anything about anyone else's secret share. And the group secret is the sum of everyone's initial secrets. What that basically enables us to do is it enables us to do threshold signing, where every party is going to participate, but no party is going to know another party's secret. And what threshold signing actually allows us to do is it allows us to, up at the top, like I said, it lets us do this space verification efficiency or space and verification efficiency. And it basically means that we now have to solve the online problem, where everyone needs to be online, which is time for another talk. Thanks for coming. That was my talk.